Welcome to the lecture on section 6.2 on trigonometric equations. What we're going to do now is we're going to learn how to solve equations with trig functions in them. We're going to look at linear methods, so we have linear equations. We're going to use the zero factor property, which we always use in quadratics. And then we're also going to learn how we might use identities to do substitutions as well. So let's look at our first problem. Solve 2 sine theta plus 1 equals 0 over the interval 0 to 360 degrees. So we know that theta is going to be in degrees. And so in this problem, it's pretty straightforward. It's a linear equation, and we're trying to solve for theta. Okay, this gives us the values, the domain of theta. And so all we're going to do is isolate theta, just like we would as if theta was an x in an algebraic problem. So the first thing we're going to do is subtract 1 from both sides. Then we're going to get rid of this 2. The opposite of multiplying by 2 is dividing by 2. And so we have the sine of theta is equal to -1/2. Okay, well, this is a known angle. First of all, we know that sine of theta is negative in quadrants 3 and 4, because theta is, sine is connected to the y value, so 3 and 4 would be where this is negative. We know that the reference angle for 1/2 is 30 degrees. So we're looking for the reference angles in quadrant 3 and in quadrant 4, so that if the reference angle is 30 degrees in quadrant 3, the full angle is 180 plus 30, or 210. And in quadrant 4, the reference angle of 30 degrees is equal to 360 minus the 30, or 330 degrees. And so this is our solution set for this problem. This is pretty straightforward. If this was not a known angle, 1/2, or we could easily use our known angle theory, we would just plug this into the inverse, the inverse sine equals, inverse sine of -1/2 to get the angle of theta, okay? And then we would be on a much more limited, even though this was over the interval of 0 to 360, we would be on a more limited domain, because inverse sine or arc sine is limited in its domain, okay? They also asked us to find, the problem didn't originally say to find all of the solutions, but if we did want to find all of the solutions, all we would do would be add n, a multiplier, and I'm talking about the letter n, times the period of whatever trig function. Since the period of sine is 2 pi, we take each of these angles and add n times 2 pi, or 2n pi, to them, okay? Oh, there it is there. That's kind of strange how it went on to the next page. Sorry about that. And I said 2 pi. Why did I did that wrong? 2 pi n would be 4 radians, and this problem was in degrees, which we knew from the original domain given. So it should be 210 degrees plus 360 n and 330 plus 360 n. If these were in radians, the 360 n would be 2 pi n. Sorry about that, guys. Even teachers make mistakes. Let's continue on, okay? So here we have sine theta tangent theta equals sine theta over, again, an interval of 0 to 360 degrees, okay? We're in degrees, so I'll pay attention this time, hopefully. It looks like it would be really convenient to divide both sides by sine, right? And then we just get tangent theta equals 1. But when we do that, we lose part of the value of the sine function in the original equation. So we have to be really careful about dividing out or factoring out or canceling out by division any trig function, okay? So a thing we might do here is try to write all the functions in the same trig function, or to try to set up something a little bit differently. Okay, so notice if we subtract sine theta from both sides, we get sine theta times tangent theta minus sine theta equals 0. And this is a place where we could use the zero property law to separate each of those trig functions into its own factor. What am I talking about? Well, notice if we factor out sine theta, we get sine theta times tangent theta minus 1 equals 0. Okay? So this sets up two problems to solve. Sine theta equals 0, or tangent theta minus 1 equals 0, which of course translates into tangent theta equals 1. Okay? Notice this is the equation we would have had if we divided by sine theta on both sides, but we would have lost the values when sine theta itself is 0 as well. Okay? And that's really important. So sine theta, sine equals 0 degrees at either, sine theta equals 0 when theta is 0 degrees or it's 180, right? This is along the x-axis. And tangent theta equals 1 when the sine and cosine functions are the same, which happens at 45 degrees, okay? Well, it also happens in quadrant 1 and also in quadrant 3. Tangent is positive, so this is a reference angle. In quadrant 1, it's the same angle, but in quadrant 3, it's 180 plus the 45 degree reference angle, okay? So here we have four possible answers to this problem: 0, 45, 180, and 225 degrees. And notice we put them in numerical order. And this is just again a reminder, if you try to solve the equation that we just did by dividing each side by sine theta, we would only have gotten half of the answers. We would have lost the sine theta equals 0 problem, okay? So for this reason, try to avoid dividing by a variable expression that has a trig function in it. Let's look at another problem now. Solve tangent squared x plus tangent x minus 2 equals 0, again over the interval 0 to 2 pi. Here, of course, the interval is in radians, so we have to keep that in mind. And if we're doing calculations with our calculator, we need to make sure we're in radians again, especially after the last problem was in degrees. Okay? I can immediately see that this is a problem that is quadratic in form because the first term is squared. But it's a little confusing for me to try to factor this. I could actually do a quadratic formula with the coefficient of a being 1, the coefficient of b being 1, and the coefficient of c being -2, which might be easier for a lot of you to do with trigonometric quadratic functions, because they're hard to kind of, I don't know, visualize. You know, we're used to something a little bit different. And so that's actually sometimes what I will do is I will convert this into a normal variable x quadratic equation. So if I think of x equals tangent x, and that's a little bit confusing, then this becomes x squared plus x minus 2. Well, this is much more simple for me to factor. This is simply the factors of x plus 2 and x times x minus 1 equals 0. Well, if I remember that x equals tangent x that I see in this first line, then I can plug those right directly into this quadratic formula and have my factors. So it might help you to do something like this little helpful hint to convert a trigonometric quadratic back into just x so that it might be easier to factor. Again, it might be just easier to think about the coefficients a, b, and c and remember the quadratic formula, right? Okay, anyway, let's continue on. So using the zero property law, zero factor property, we can know that we can set each of these factors equal to 0 and solve. Tangent x equals 1 or tangent x equals -2. If we look at the first one, tangent x equals 1, This happens in quadrant 1 and in quadrant 3, and we get the values of pi over 4 and 5 pi over 4, which is of course equivalent to 45 degrees. These are the places where sine and cosine are equal, because tangent equals sine over cosine. So in order for this to equal 1, their values have to be the same. Okay, we already did this in the last problem, but we did it in degrees, not radians. But now let's look at tangent x equals -2. Okay, for tangent x equals -2, now we're going to need to use our calculator and figure out what the inverse tangent of. We're trying to find the angle, right? So if we take the inverse tangent of -2, this will give us the angle in radians. Now make sure your calculator's in radians, etc. So notice when we do this, we get, I'm sorry, I just went blank. We get an answer in quadrant 4, but it's not in 0 to 2 pi, right? It's a negative value. So I really need to do a couple things. First of all, tangent is negative not only in quadrant 4, but also in quadrant 2. So I have to do a couple steps here to kind of finish solving this problem. First of all, I need to add pi to this value, to this angle value, to find my angle in quadrant 2, okay? I also then need to add 2 pi to this value, because notice this value is not between 0 and 2 pi, it's negative. It's not in the domain that we were given. So I need to add 2 pi to it to get to a positive quadrant 4 value, a coterminal that's between 0 and 2 pi, not a negative value. And so that's why we add pi and 2 pi to that original answer we found, because this isn't inside the domain of our problem. Remember, our problem said find all answers between 0 and 2 pi. Well, this is negative, so it's outside of that. So we had to add 2 pi to find the positive quadrant 4 value, and we just added pi to find that same value in quadrant 2. So ultimately, these are our 4 answers. These were the 2 from the previous page, and then of course the 2 we just figured out here that you can see on this diagram. Find all solutions of cotangent x times the cotangent x plus 3 equals 1, and then write the solution set. Okay, so we first have this cotangent x times cotangent x plus 3. Makes sort of sense to kind of multiply through, and so we get cotangent squared x plus 3 cotangent x minus 1 equals 0. This might be another good place to rewrite this as x squared plus 3x minus 1, okay? But I can immediately see that when I have a minus 1 at the end, there's going to be no way that I'm going to be able to build a 3x in here. So this is probably one that I want to use the quadratic formula with, because I cannot factor this easily. It might be easier for you to see this as x squared plus 3x minus 1. I mean, there are no factors of -1 that are going to add up to 3. Okay, so here we have a equals 1, b equals 3, and c equals -1. And so we plug these into the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac over 2a. You may have heard the old story, but anyway, this isn't the class to teach you the quadratic formula. You should know this already. When I solve this, I get -3 plus or minus the square root of 13 over 2. So these are 2 possible answers that I'm going to get. So I have the cotangent equals -3.302, etc. Or the other value when I solved the quadratic formula was cotangent x equals 0.302775, etc. Okay, we're trying to find the value of x, so we really need the arc cotangent. These are radians, they're not known angles, they're not exact measures, so we're going to have to use the inverse tangent button on our calculator. Okay, remember that that in order to do that, we have to take the inverse tangent of the reciprocal. The inverse tangent of the reciprocal cotangent value. So we get the inverse tangent of 1 over negative 3.302775, or we get inverse tangent or arc tangent, of 1 over this number. Okay. Now you may notice that in this first problem, we have plus pi here. Now why do we have plus pi? This has to do with the fact that we're using the inverse tangent to solve this problem, and it's an inverse cotangent problem. Remember, cotangent, inverse or arc cotangent, the domain of that is quadrant 1 and quadrant 2. Specifically, quadrant cotangent is negative in quadrant 2. However, because we're using our calculator, we had to use the inverse tangent button, and tangent is negative. Inverse tangent, is limited to quadrant 1 and quadrant 4, and it's negative in quadrant 4. So we're looking for a value in quadrant 2 for cotangent, but the calculator is going to give us a value in quadrant 4 because we're using tangent, and it knows that arc tangent is in quadrant 4. So we have to add pi to go from quadrant 4 to quadrant 2. Okay? So we solve these, and we get these two values of x. To find all solutions, so really what we're looking for are all the coterminal angles, we simply add integer multiples of the period of whatever trig function we're dealing with, and here we're dealing with cotangent, which has a period of pi, so the solution set is 2.847 plus n pi, and 1.276 blah 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 plus n pi, where n is any integer. Okay? Hopefully that helps. And this is a really weird condition, but you got to be thinking about, especially when you're dealing with inverse trig functions, what is the domain of that? What is allowable? What quadrants are those functional values allowed? Okay, let's try another one. This is an interesting problem. The tangent of x plus the square root of 3 equals secant x. Okay, so this it's not a quadratic. Looks linear of sorts, but there's a radical in there, so not quite linear. And we have tangent and secant. Okay, when we're trying to solve equations, we really are either trying to get each trig function in a factor by itself, so we can use the zero factor property, or we're trying to get rid of one of the trig functions by doing substitution, like tangent equals sine over cosine or something like that. Okay, in this case we can also think about our identities. What identity has tangent and secant in it? Okay, and if we do that, then we can probably substitute out one of those values. Okay, well, remember we don't have anything that relates tangent with secant, but we do have something that relates tangent squared with secant squared. So here I'm squaring both sides of the equation, and again, because I remember that there is a identity that connects tangent squared and secant squared. So when I square the left side of the equation, I get tangent squared plus 2 times the square root of 3 tangent x plus 3. You're like, what? Where did that come from? This is just foiling this out. Tangent times tangent, tangent squared. Tangent times square root of 3, square root of 3 tangent x. Do it the other way, square root of 3 tangent x, 2 of those, so multiply by 2, and then square root of 3 times the square root of 3 is just 3. Okay, this is just a FOIL of this square. Be careful, a lot of students try to move in a hurry. They square the first term, tangent squared, square the second term 3, and forget about the middle term. You cannot do that. That is not how FOIL works. And then, of course, on the right, we just get secant squared. Okay. Well, remember that secant squared equals 1 plus tangent squared. That's one of our original Pythagorean identities. Okay. So now I have tangent squared. I have the left side equals 1 plus tangent squared. Well, notice if I subtract tangent squared from both sides, these cancel out. And I'm left with 2 square roots of tangent x plus 3 equals 1. If I subtract 3 from both sides, I get this next line, which is 2 times the square root of 3 tangent x equals negative 2. Okay, again, I'm trying to get tangent x by itself, ultimately to get x by itself. So I'm going to, the opposite of multiplying by 2 times the square root of 3 is dividing by 2 times the square root of 3. And so I end up with negative 1 over the square root of 3. You can rationalize this, but honestly, I would leave it like this because this is easier for me to see. Specifically, what this is a known angle with a 30, 60, 90 triangle. And so it's easier for me to see this in terms of the sides and knowing that tangent is opposite over adjacent. Okay? But in trig we rationalize the denominator. But since I'm still trying to solve it, honestly, I would leave it in this original form. Okay? Tangent is negative in quadrants 2 and quadrants 4. And so our two possible solutions for this are 5 pi over 6 or 11 pi over 6. Okay? Now, one of the things that happens is when we do something like this where we square an entire equation or squaring each side, we have to check the answers, because when we square things, like when we square, especially if we square negatives, they become positive. And so we create what's called false positives. And it really has to do with that idea of squaring negative numbers, that will create solutions that work within the square, but they don't work within the original equation. So whenever you square an equation, this goes beyond trigonometry, whenever you square an equation trying to solve for it, you really have to go back and divide, let me say divide, excuse me, sorry, need more coffee, and check each answer. So let's go ahead and check each answer. All we're going to do is plug those values into the original equation and see if it works. Notice when we plug in 5 pi over 6, this does not work. And here we get positive on one side and negative on the other. And this is the problem, because if we squared both sides of this, then they'd be equal. And so that is literally the history of why we call them false positives. Okay? So 5 pi over 6 is not a solution. Let's plug in 11 pi over 6. And here we get the correct answer. So our only possible solution to this problem is 11 pi over 6. Okay? So let's just kind of review what we've talked about and how to go about this. When you're solving a trigonometric equation, first look at the equation and see what it looks like in algebraic form. Is it linear or is it quadratic in form? This will be a first kind of determiner for how we're going to solve this problem. If you have only one trig function present, first solve the equation for that function. If more than one trig function is present, see if you can rearrange the equation so that one side equals 0, and then see if you can factor it with one trig function in each factor. And that's another way if you have multiple trig functions. If that doesn't work, then you can do what we just did in the last problem and look for identities that you can use to substitute in and get rid of one of the trig functions. If the equation is quadratic in form, but you can't factor it, we saw that problem too, just use the quadratic formula. And again, make sure that all your solutions are in the right interval. Try using identities to change the form of the equation. We saw this as well. It may be helpful to square each side. We saw that as well. In this case, when you square each side, make sure you check for extraneous solutions, or false positives.